Hey, let's get started. I was just muting. Welcome to Material Science Department. I'm He Qian, your moderator today. We also have Prof. Xue Junmin and Prof. Stephen Adams. Prof. Xue will firstly give a brief introduction about our MSc program in the Material Science Department. Then, which is about 10-15 minutes. Then Prof. Stephen Adams will give a brief talk about the high performance energy storage, just to give you an idea what material science is all about. Then we'll use the rest of the time answer your questions. All right. Without further ado, let's welcome Prof. Xue Junmin.
Good afternoon, everyone. So welcome to the MSE, so MSc program. Okay, I'm Xue Junmin. Okay, the deputy head of the postgraduate program. I'm in charge of the MSc, this program. Okay, so today I would like to give you a very brief introduction to our department and also our MSc program. Okay, so actually I can see some names are quite familiar. So I believe that because we have done several such the introduction already, so some student may be familiar with me already. Okay, thank you. So to start with, okay, let me quickly highlight two very important number of our department. Okay, so the first number is about our department ranking. Okay, so in a recent or most updated QS, the World University ranking, MSE is ranked as number 7 in subject materials science. So actually this is a very good ranking. Okay, so and the second number I would like to highlight is about our employment opportunity. So we are ranked as the number 1 in terms of employee ranking in Singapore and Asia. Okay, so this also indicate our department, the students are very popular in the Korean market. Okay, so for the staff, now we have more than 30 academic staffs in our department, including assistant professor, associate professor, and full professors. And this slide, okay, just a very quick the glide to see the names of each one. But of course, if you want to know more details of each professor's research work, please go to our website and find out their personal web page. Okay, so in general, we have a very strong academic the education team. So most of our faculty member staff, they are recognized as global top 2% research leaders in their respective research area. Okay. And among all staff, okay, I would like to highlight one very important staff for our department. His name is Professor Kostia. We call him Kostia. Okay, so he is the winner of the Nobel Prize in 2010 for physics. Okay, because of his discovery of graphene material. You know, right? Most of the students should be familiar with graphene material. It is a 2D carbon material. Actually, Kostia is the person who discovered this material. And now he is the full-time professor in our department. Recently, good news is he received a very large the funding to establish a new institute which focuses on functional intelligent material. Okay, so the funding support is huge, I can say. Okay, 200 million Sing dollar. Yeah, so for the institute. Okay, so and also I would like to highlight some achievement of the professors. Okay, some of you may be familiar with the highly cited researchers every year. So worldwide, so the publications of professors will be compared, and also will be calculated how much citations they have received. Okay, worldwide, okay, there are 6,600 scientists. Okay, they are recognized as highly cited researchers. That means their publications are highly cited, and also this indicates they are the pioneers in their research area. Okay, so NUS, okay, the NUS we have 32 among the 6,600. We have 32 professors are recognized as highly cited researchers. But in our department, as a single department, our department has 5 professors. Okay, they are recognized as highly cited researchers. Okay, in their research area. Okay, so their names are here. So this is also the very important indicator showing the strength of our department research. Okay. So in general, our department now is focusing on the 4 big research areas. The first one is energy sustainability. The second one is AI, data analysis. And the third one is biomedical material and software robotics. The last one is the advanced materials and the microelectronics. Okay, so of course, again, if you are want to know more details of our research activities and our focus, please go to our department website. Okay, to get more information. Yeah. Okay. So let me go through quickly about our MSc program. Okay. So MSc, the full name is the Master of Science, the program. So this is a 1-year coursework program. So this is a 1-year program. The student, to get this degree, you must complete the 40 modular credits. So in NUS, most of modules carries 4 credits. So that means the 40 modular credits means that you need to complete 10 modules usually. Okay, and also there is a minimum requirement to get a degree. So in NUS, we call the CAP system, Cumulative Average Point system, grading system. Okay, the full mark is 5, but if you want to get a degree, you must get a minimum 3. Okay, so 3 is about B minus. Yeah. Okay, so and also because some students like to have some research experience. Okay, so at the same time, also in our curriculum, also we provide 2-semester research project. So actually, this is we consider as a module, but the student can get the research experience with professors. Okay, this is a module, but also is a research project. You need to work with professors in their research lab and also to submit report. Also can consider as a kind of the thesis. Okay, so this research project comes as 2 modules, 8 MCs. So some student will choose 8 normal modules and plus 2 the project, plus 1 project equals 2 modules. Okay. So our curriculum, okay, our curriculum there are many modules you can select. Okay, so in general, all the modules can be divided into 3 categories. The first category is called the core modules. We have only 2 core modules. These 2 core modules are the foundation of the materials science and engineering. So of course, some students will tell me, okay, so you have learned similar modules in your UG study already, right? So do I still need to repeat these modules? My answer is not necessarily. Okay, you can put up a request, then you can waive these 2 core modules. To waive these 2 core modules does not mean you can choose less than 10 modules. You still need to complete 10 modules. Okay, you must choose another 2 modules to replace these 2 modules. Okay, so for the details of the curriculum modules will be discussed again next week. We'll call another meeting, Zoom meeting, so to discuss about the curriculum and also module selection. Yeah, next week. So the second category of our curriculum is the MLE elective modules. So here we provide more than 10 modules here. So covering from the energy, modeling, nano, right, and also polymer, and also the structure of material. So these are the modules belong to the MLE elective modules. We have the last basket is the general elective modules. So this also include many of our own MLE modules and also include some modules from other departments. Okay. So our department And for this, the MSc program, so far we have 2 specializations. Okay, so the first specialization is called Advanced Materials for Energy and Sustainability, and also we have the second specialization is the Materials Entrepreneurship. So we are having more. Okay, we're having more. So, but so far we provide these 2 because we are creating more specializations in this program. Okay. So for the first specialization, energy and sustainability, so this is the basic requirement. If you want to specialize in energy and sustainability, you must complete 20 MCs, okay, from this basket. Okay, so this is called energy basket. Okay, so to get the specialization, in total, you still need to complete 40 MCs, but 20 MCs must be from this basket. This basket, all the modules are relevant to energy study. Okay, so here we also must pass through a compulsory module, thermodynamics for sustainability, and also all the modules about energy here. Okay. The second specialization is called entrepreneurship. Entrepreneurship is also quite special and unique in our department. So students are encouraged to take this specialization beyond the normal, the materials, the knowledge. Okay, so similar. Okay, to get a specialization, you still need to complete 20 MCs from this basket, which is called entrepreneurship module basket. Okay, so of course you need to pass 2 core modules, and also you must select the modules from this elective basket. So in total, you need to, if each module is about 4 MCs, and you need to complete 5 modules for this basket. Yeah. Okay. So actually, this is the curriculum. Actually, this is my last slide. So I don't have too much to say. So this is the last one. Thank you very much. So we have the Q&A session later. So after Professor Stephen's the presentation, we will have the Q&A session. If you have any questions about curriculum, please you ask, we will answer. Yeah. Okay. So thank you very much. Yeah. I'll stop share now. Yeah.
Thanks, Prof. Xue. So I think let's carry on with the presentation. If you have any question about the application, you can ask later or type it in the chat. We'll come back to it. All right. So now let's welcome Prof. Stephen Adams. So he'll have a talk about high performance energy storage for sustainable future. So let's welcome.
Hey, thank you, Etienne. You have seen energy storage and sustainability are the focus area in our department, also one of the specializations. You may also see me next year as giving the lecture on the energy storage and conversion in the master program. So I would like to give you a bit overview of what is the research area we are working in, and so there are a number of people in the department working in this area. Lithium-ion batteries have modified quite a big part of our life. So all the portable electronic devices nowadays, you will see the higher value ones are powered by lithium-ion batteries. But what really drives the development in energy storage are 2 areas. One is electromobility, like this one. This car is actually just retired now, so they stopped producing this one, came with the next generation already. And the other area is more efficient use of renewable energy resources by intermittent storage. We talk about electromobility, so you may know this car brand, but this is actually one of the most old-fashioned car brands. So you see their battery pack has thousands of these small batteries, and what we are looking in now in the rest of the slides mostly is just one single such cell. Most other brands have much bigger batteries, but the systematic setup is essentially the same, just less of dead mass this. So why is this not good enough? Why do we need other batteries? So we need safer batteries. You all know this fires, laptop fire may be a nuisance, but a PMD fire is already life-threatening. And also from a commercial point of view, if you see all these buses here, and a minute later they look like this, and then 15 minutes later they look like this. So that's a few $1 million lost. Also, we need other batteries that are more sustainable than current ones. You have here a periodic table, and only a subsection of them, essentially the greener the better, are suitable for large-scale technologies. So here for the anode, we probably need these lithium or sodium or maybe magnesium. For the cathode, we need probably the oxides of these transition metals. You see there's some green, but most of those currently used are at least yellow or some orange, so very supply constrained already. Lithium, actually, there's enough lithium in the world, so that's not the problem, but the geographical distribution of where the lithium comes is not so ideal. So most of the technically valid or valuable lithium is here in this so-called lithium triangle in Chile, Bolivia, Argentina. And there, that's a very dry region, Atacama Desert. So there, the huge amounts of water that are needed in the processing of the lithium, that's the real environmental challenge here. And material that is extremely supply constrained is the cobalt. So more than 90% of the world's cobalt comes from one country, Democratic Republic of the Congo. And that's how the mines look like. This is not really a safe working environment. So that's just picking up the last crumbs of these materials that are available, so that people just jump into these mines and hope to survive until the next day. And then the material goes to China for refining. So most of the value is not benefiting these people in Africa, but later in the processing chain. Nickel is something very important for the region. So if you don't want to use cobalt, the next candidate is nickel, and the country with the largest nickel reserves in the world is Indonesia. And so you can see all the companies knock on Indonesia's door and try to get the nickel reserves from them. But nickel now, Indonesia says, no, we are not interested in delivering just the nickel ores. We want to have the value chain in Indonesia. So we want to have the refining and maybe also the battery production there. We'll see how this develops. And another source of material will in the long run have to be the recycling. Just to mention, that's done currently in a very rudimentary way, essentially to get back the cobalt or some of the other metals like copper that's used here for the current collectors. But much more can be done here, and also the non-metallic components could be recycled. How does a battery in principle work like? Very easy. So you have a redox reaction that you force to run in a special way. You have some very strongly oxidizing material, like here oxygen or chlorine, and some very reducing material like lithium, magnesium, aluminum. And then if you bring them in contact, they would react immediately, but you separate them and just let the ions move through an intermediate medium, the electrolyte, and the electrons have to go by an external circuit. And then from the different tendency of the materials to attract electrons, you can calculate what is the voltage of this battery. Not a new principle. So the first batteries looked like this, that were the voltaic pile by Alessandro Volta about 220 years ago. So the more modern batteries may look in principle like this one. You have this oxidized material and the reduced material here. And when you then let the system discharge, so here the lithium can move from the graphite into the transition metal oxide. So now you have two materials which are somewhere intermediate in oxidation power. And when you charge them again, you have really some strongly oxidizing material, some strongly reducing material again. That's the so-called rocking chair principle that was introduced by Michel Armand. But 3 other people got the Nobel Prize for this. And why was that? So 2019 chemistry Nobel Prize was for lithium-ion batteries. First person here, Stan Whittingham. He came up with the idea that of the insertion or intercalation materials for the cathode. So his material was lithium titanium sulfides. You have a material where you can don't have to break any bonds, but you can still stuff in some lithium ions into gaps here in the structure. There's a major advantage because then you have this rocking chair principle. Lithium can get in and go out without much disturbance to the structure. But this has only about 2 volt. John Goodenough then came up with the idea that, we cannot increase the voltage of the sulfides, otherwise the sulfide will become sulfur, will just be oxidized. But we can go to oxide materials, so transition metal oxides. There we can go up to about 4 volt before the oxygen is being oxidized, or the oxide ions are being oxidized. So that's why he suggested lithium cobalt oxide, and that was also one of the materials in the initial batteries. So that caused all the problems with the cobalt that we now stop by getting rid of the cobalt in the structure. And the last person here is Akira Yoshino. He introduced the anode material. So he reduced some carbon-based anode material. So it's safer and a bit easier to work with, not with the lithium as the anode, but with a low energy or low potential material, which is close to the potential of the lithium. And currently this graphite is used. That was not his material. That was actually introduced by Rashid Yazami here from Singapore and Jürgen Besenhardt from Germany, but a similar material was already introduced by Yoshino. And why Yoshino was picked, because he was also the patent holder for the first prototype combining all these right materials, and was also leading the commercialization of the material by Sony. So then we have this anode material, cathode material. You need to connect them by the electrolyte that has to be stable against reduction, stable against oxidation at the cathode, has to conduct the lithium ions from one side to the other one, but it has to block the transport of free electrons, so the electrons have to go through the outer circuit. And you have to add a kind of porous medium, a separator, so that the anode and cathode cannot touch each other, because this gap here will be very small, typically around 20 micrometers. So which electrolytes are used? Organic materials, because if you use water, that would just be decomposed at these voltages. And then you need a salt in it, lithium, of course, lithium salt, but the anion should be a large anion, low charge anion, so that it has low tendency to be bonded to the lithium, so that it's easily dissociated. This condition never works perfectly. So the reduction at the anode always happens to some extent. But fortunately, and that was found by Jeff Dahn here, there's a kind of self-limiting reaction. So you have initially some decomposition, but that creates a layer called the SEI layer that then protects the anode from further attack. How was this developing over time? See, if you have these blue points here, you can see we have this graphite transition metal oxide batteries, how the specific energy density the kind of leveling off, and you can say around 300 is the theoretic maximum, whatever material in this class you pick, as long as you use graphite as the anode. But in the meanwhile, in academic research, you have a lot of trials to go to higher energy density. And fortunately, in this review, NUS is listed as the world record holder, so with over 400 watt-hour per kg. But these cells are not very stable. And this is only possible when you go away from the graphite anode and go to the lithium metal or lithium alloy anodes. So you want to go to higher energy density, higher power performance. And a way to go to higher energy density is to have a more stable electrolyte. Because lithium metal and the normal electrolytes doesn't work. So you need other electrolytes, and one class of material that can be used there are all solid state batteries, where it's a solid material that acts as an electrolyte. It's also not typically a non-flammable material, which also would solve the problem of the fire hazard. It can be more dense, energy dense, because see, if you replace the graphite here by lithium metal, that for the same energy density requires much less volume. Your liquid electrolyte, you have to make the solid electrolyte thinner, and probably so thin that even the higher density doesn't matter too much. And a good part of the advantages comes also from the fact that nothing can leak here, so you don't have to wrap each single cell. You can stack them one by one and have one large stack, so-called bipolar design. Okay, everything sounds ideal, but we don't see this in the market. There must be a reason. So there's still a number of challenges that have to be overcome. So things that work automatically in the liquid electrolyte batteries, now we have to take care of ourselves. So first of all, ionic conduction has to be fast enough. So you have to find good ionic conductors. Then all these interfaces, you have to ensure good contacts. You have to prevent that the lithium metal or sodium metal or whatever can grow through this powder or through this ceramic to the opposite side and short circuit the cell. I think that's the main challenges. First of all, we have to understand this. So that was one work from also published last year by us. So where LAGP is one such solid electrolyte, a good electrolyte, but not so stable against lithium. You can see after being exposed, there's some decomposition, see here by the other element distribution. But the bad thing about this is that the decomposition products then need more volume than the original phase. And it is this increased volume that then causes the real cracking of the cell. So you have to understand that it's not enough to see, there will be some failure of the material and we can live with a certain amount of failure, but we have to design the way in which the material fails. It should fail here into phases that don't require more volume. Okay, we said about addressing these challenges like better electrolytes or better interfaces. And we should do this not by random trial and error, but by a systematic choice. And we came up with a software that, at least for the solid electrolyte design, can help a lot to accelerate this development. Before talking a bit more on the electrolyte, we should say that electrode design, same thing. The rate performance of the intercalation electrode materials is again limited by the transport of the lithium or sodium ions within this material. So it always has, if you want to charge faster, then capacity will go down. So always this sigmoidal curve. But the activation energy or the migration barriers will decide where this point is, where the capacity goes down. And there are some other structural factors that can then decide this slope. So we can, in the meanwhile, understand why these curves look like that. And when we look at the structure, we can already predict these curves. So that's why we can shortlist then good materials. Here, one example, lithium iron phosphate, very good. Cathode material, sodium iron phosphate. This is crystalline sodium iron phosphate, very poor rate capability. But if you make it amorphous, much better rate capability. So, and here the data points are the experimental measurements. The lines here are what is predicted from this model. What we want to do is have a high throughput screening so that we can cover not individual compounds, but whole classes of compound here. So entire phase diagrams can do in one afternoon. And so that's actually achieved now. One of the major phase diagrams that we have to look into here, which has the most promising materials, is this lithium sulfide, phosphorus sulfide, or other high oxidation state sulfides, and lithium halides. And there are a lot of the now studied materials are in this area. So the main classes of oxide and sulfide. So electrolytes are listed here, and just to mention all the ones with the blue markers here, then where our group here at MSE contributed to their understanding. So, and this is the conductivity achieved by liquid electrolytes in the batteries. So you see some of the solid electrolytes now are better ionic conductors than the liquid electrolytes. Example here is the sodium tin antimony sulfides. So that was at that time the fastest sodium ion conductors. Maybe we can go a bit faster. So, and then we came up with a new class of sodium all solid state batteries. Maybe we skip this. Just to mention a bit on, yeah, we have a new material, but then to optimize the material, we may need to dope it. And this doping, for example, we can also automatize. We can have an automatic dopant predictor that was introduced in this work. And you see that was published last year. And now all these people are, except me, who is still here at NUS, spread around all these companies. And so you can see which dopant will go on which side, or how much of the dopant can be dissolved. If we look into the achievable energy density, we have to make the material very thin, understandably. So we can either do tape casting. So ceramic alone is often not so good. We can make it much thinner when we combine it with the polymer here by tape casting, or by 3D printing, or by spin coating, very traditional technique, but you can make very thin layers here, half as thick only as the liquid electrolyte layer, and that's where we really have to be. And then we can make nicely cycling batteries. And so this is a lithium air battery that we used for that. Maybe just last area interface. So a big area is now to optimize the interfaces here to protect the lithium metal here from polysulfide, just one example. And without coating, after a few cycles, the capacity goes down drastically. With the coating, with here's atomic layer deposition, you can get a much more stable cycling. We do a lot of simulations, and last thing I want to mention is here, this is a master project from last year. Yuan Pu introduced a new machine learned force field that is able to better describe these interfaces, very fast force field, but still highly accurate. So you can study things like the surface relaxation or the surface evolution, and then use it also for device level simulations, where in this computer you have the entire anode, electrolyte, cathode system, and can really understand the interfaces better. And with that, I should, I think, come to the end of the talk.
Okay, thank you, Stefan. I think I don't know how long the breakout room will last, but if the breakout room ended, please go to the main room. There will be another session at 6 p.m. Now, we welcome any questions that you may have about the material that you just heard or about the application. Junhao asked, what is the admission criteria? Prof, do we have the latest?
So admission criteria, actually, basically we look at the English result first. You must have the IELTS or TOEFL result. Okay, and also you must have a successful, good average score of your university bachelor degree. Yeah.
You need to come with sort of a relevant background, right? You
yes,
need to have chemistry, physics, chemical engineering, material science, BSc degree. Otherwise, you will not be able to follow the curriculum. Hope that answered your question, Junhao. 3.2 out of 5.
3 point should be okay. Junhao, you are from our department or you're from MSc? No, NTU. 3.2 can. 3.2 you can try. Yeah, yes. And yes, NTU MSc you can try to apply. Yeah, okay. So actually we have the 2 admission period, the intake. The coming one is the general intake 2023 and August intake 2023. But we have opened early admission for the 2023 August. Yeah. When will the August 22 session come? What do you mean? You mean apply or start?
Start.
The first week of August semester start. Yeah.
Yeah, the session will be closing in a minute. If you have questions, feel free to email us.